information that will help you in your exercise. When it comes to observation of climate system, including the water sector, a lot of information nowadays coming from satellite, and there are a lot of satellites out there in the space, and the data are actually available to all of us. In the past, only satellite mission from USA was in public domain, but nowadays the Europeans have also shifted and they have made accessible all the satellite information. So here, what you see is NASA missions. Just a little snapshot, it's not all, that shows different satellites over a different period of time. You can see Aqua Modus, for instance, here. By the way, do you see the cursor, my cursor moving on the screen? Are you able to follow my cursor? You know, I have a pointer which I'm trying to move around. Is it visible?
It's not moving.
Not moving.
So I don't know how to do that on Microsoft Teams. Anyway, I hope I will be slow, so you should be able to pick from what I'm talking. So there are different satellite missions here. For instance, SMAP is a soil moisture satellite, measures soil moisture. Landsat, land surface signals would be anything that you find that provide signature to satellites. For instance, Landsat have different spectral bands, and a lot of things that are available on the ground, they have different signature. Yeah, they are sensitive to different bands, and combining these bands will provide some basic information. GPPM down here at the bottom of the screen is a global precipitation measurement mission. This is now providing a lot of high resolution precipitation information. So there are many of them out there that we can easily access, and the exercise that I sent you yesterday, perhaps you received this morning, is mostly how to explore these resources for your science, actually. I believe that you have different interests and different topics for your PhD studies, and you'll find definitely something that is useful to your cause. Here are the satellite missions for ESA, European Space Agency. Actually, there are different satellite groups here. Science mission, as you can see, there is a science mission. There is a lot of application satellites for Earth observation. Copernicus, under the name of Copernicus, it's a series of satellites. And you can see that beginning somewhere around 2010, yeah, there is an evaluation going on from 2010 on the screen at the top right corner of top left corner of your screen. Moving towards your right side of your screen, you find 2015. This shows how the satellite evolves. 2020, 2025. Actually, this is future missions which are in plan on the ground, but the launch date is expected to be around 2025. And they have already some satellites that they are working on, because satellites are not just sent out to space, but there is a lot of testing going on the ground, and usually it takes quite substantial time to develop a single satellite. Would take anywhere between 2 to 10. Some complex one will take up to 15 years of preparation before they are launched. So they have also this satellite with non-scientific mission, mainly meteorological mission, Sentinel-5B, MET-G13, Sentinel-4B, MET-G52. If you look at on your screen on the right side at the bottom, these are the satellite in yellow, in orange color, that to be launched in 2030. So there is a preparation going on. They know exactly where they're going, and a lot of data are available. Most of these data are available to you, actually, if you use these science data platforms. Now, just to give you a snapshot of the satellites used, for instance, on this slide, water available products, water-related products from space, for instance, latent extent, river widths you can get from Landsat. You look at the table at the top corner, top left, from MODIS, with a resolution of 250 meters, Landsat up to 30 meters. And that time period, you can see it's very extensive. For instance, for Landsat, it starts from 1972 up to present. And frequency of data delivery is 16 days. MODIS is a weekly data, because these are not geostationary satellites. These are polar orbiting satellites. That means they will be at different locations at different times. The geostationary satellites are those which are fixed in space and are rotating at the same speed as the Earth's rotation. So they will appear to be in the same location. They'll be stationary. So that's why a given geostationary satellites, let's say it tended to look at Africa, will be located at a certain longitude latitude, so that every time they will be at the same location. And you have to have a series of geostationary satellites to cover the whole globe. But for the polar satellite, polar orbiting satellite, a single satellite will cover the whole globe. And of course, the coverage to come to the same place, for instance, in the case of Landsat, it will take 16 days. In the remaining 15 days, they will be somewhere else. Yeah, come back to the same location. You have to wait for 16 days. That's what it means. Otherwise, the observation is continuous. The sampling is almost every few minutes, in some cases, even second in some cases. So there is a continuous observation, but since these are polar orbiting satellites, they come to the same location after an interval of time. You can see other satellite which looks at, let's say, lake and river surface, water elevation, such as TOPEX, Posodium, JASON, Japanese satellite, Sentinel-1, Sentinel radar. It's a radar the same signal. These are active remote sensing. Sentinel radar altimeters. Sorry. And the spatial resolution is 0.1 degree. You just have to multiply by something around 110, and then you get this around 10 kilometer resolution, basically. 0.1 degrees around 10 to 11 kilometer. And the information is about from 2000 to present. We have a lot of data. And then the temporal resolution is 30 minutes. So this is a consultation of satellites. So that's why they are able to look at same data. Snow cover could be from MODIS. We are not interested in snow cover in Africa, obviously. Not many places have snow cover except some peak mountain areas in East Africa region. Surface soil moisture, AMSR2 is an European satellite. SMAP is American satellite. You can see the resolution from 9 to 25, 9 to 50 kilometers. And the data coverage goes, for instance, for AMSR from 2012 to present. And the the data frequencies on a daily basis. GRACE, which I'll be showing some example, GRACE FO and GRACE. These are satellites that looks at terrestrial water storage anomalies, and the spatial coverage is somewhere from 0.5 degree or an area of 150 kilometers squared. And you can see the temporal coverage, GRACE. The oldest one is from 2002 to 2017. The newest one is from 2018 to present. Now, usually some of these satellites they have limited lifetime. So you have to plan a follow-up mission, satellite mission, that will continue from where the other stop working. Sometimes this is not precise. There could be an overlap. There could be even a data gap depending on the success of the satellite mission. And the data delivery is a monthly data, and there are so many of them. You can also look at other geophysical variables such as vegetation index, crop water demand, evaporation, surface temperature, and you can see the spatial resolution, the period, frequency. Of course, as I hit this talk is recorded. You can come back again and look at them. And other things like water clarity, is about water quality, chlorophyll A, suspended sediment, usually from sea waves. It's American satellite. This has been delivering data every 2 days over a given location, mostly focused on the sea, on the ocean. Aqua is it has most, well, we have Aqua Terra and Aqua Modis, Aqua and Modis Terra. One is for the water, other is for the land, and the data coverage is started in 2002 and it's going on until now. So there are different parameters that you can get from this one. So mostly what you see here is about water quality. You can monitor water quality of a lake, and I will show you later on an example of what we have done with my work. So these are the information that are available if you are able to access what I'm going to show you in the next slides. This is an example of GRACE, total water storage anomaly derived from MODIS. You can see this is basically an index ranging from somewhere -2 to +2. Wetter than normal condition is in this range here, 1 to 1.5, the bottom, to +2. Normal is between -1 to +1, and drier than normal is shown by -1.5, from -1 to -2 over -2. So these are an index. This is an example from a presentation I gave somewhere. In another talk, you can see clearly the blue ones are where you have excess water storage, and the red ones are where you have deficit water storage. So this is for East Africa. Unfortunately, I've been done for the Southern Africa region, but you can go and try them in the platform I'm going to provide you. So for GRACE, for instance, for your region, the best example is this is a drought of 2015-16, yeah? And this is a Gaborone Dam in Botswana, which supplies much of the water for Gaborone City. And you can see that yeah, on the right top corner of your screen, you can clearly see the dry part of the dam shown by dark color. Well, the water exchange, sorry, Dark color was the water level, the water extent in 2011, for instance. As you go toward this white color, that is the case of 2015. You barely find water at the center of the dam. GRACE can also pick the height variation of the water, as you can see on the top left side of your screen. It's a line graph. It starts from 2008 GRACE measurement up to, you can see the data range is from 1992 to 2024, but the data is available only from 2009. So you can see clearly the water level is here at 995 meters above mean sea level. And you can clearly see as you go approach 2060, it went from 900 around 995 meters to somewhere around actually below 980. It's less than decrease in almost by 50 meters. So this valley down here, close to 2016, is the peak of the dry season, the peak of the dry period, not season actually. This is an event that happened maybe 100-year event, because this is very extreme dry, which affects the whole region. And in fact, this kind of satellite can also be used, not only the severe hazards, but also something related with, let's say, construction of new dams. And this is the water level where a new dam is built by Ethiopia over Nile Basin. You can see that naturally the river, the place where the dam is built, the water level fluctuation over years, long time. You can see it's a Nile River, Blue Nile, and it fluctuates around 560 meters above mean sea level. As the dam starts filling up, it goes all the way to 590. So a change of about 30 meters, because this is a very big dam, which will generate a lot of electricity. I expect to go up to from river level, which is 560, it will go up to additional 100 meters because it's going to generate huge mega power of electricity. So you can monitor a lot of things with this kind of satellite, and the tool that I'll show you is useful to do this kind of analysis. So back to the exercise I provided you. This is a screenshot of the platform. It's called Giovanni. It's a bridge between data and science. It's a tool. You can see at the top left corner, the word Giovanni is sponsored by NASA, and it's called Earth Data, NASA Earth Data. And if you look at the top right corner, you see feedback, help, and then toward the end you see log out. Now the screen shows that I logged in with my username, Gizao M. That's how I created my username. And of course, you can access this science data without registration, but you are not able to produce any figures. You can just look at them like at Apple's here. When you plot and they want to download the data, it's not possible. So it is important for them to track the number of users. And for instance, in case your work led to some kind of publication, that you have to acknowledge the data source, because they are not doing for free. Of course, it's free, but You just have to recognize them that you use their data. So that's why registration is important. It takes you a few minutes to register, and actually your account will be active immediately. It's automatic approval. Nobody on the other side has to check what you requested for. You just give some small details and you get the account. So once you get the account, you log in and you see this kind of a screen. Of course, this blue list with a box in front of it are based on the search I gave. Since in this class we are interested in hydrology, for instance, what I did was I went, for instance, to select variables. There are different tools. Under observation, you have model. About in this figure, if you are able to see, there are about 430 model data, 430 different kind of model data that are usable. These are not just model, but these are a reanalysis model combined with observation. So they are more or less like observation. All you need to do is make sure that these models have achieved the required level of accuracy from literature. So they are not just models like doing some kind of scenario or simulation, but these are reanalysis. Wherever there is observation, observation is taken up, and where there is no observation, model will take over. So it's a kind of tuning the model with observation, and precisely where there is observation, the model gives you exactly the observation itself. It doesn't change. But where there is no observation, it will use the observation from different points to estimate the value at other points where there is no observation. So down, I ticked this one. It's shown in orange color, and there is a tick mark there. And then observation, under observation, which is purely observation, you have 65 of them, 65 kinds of observation under hydrology, actually, because we also ticked hydrology. We also ticked hydrology, as you can see, and then that's why you see this number of observations. So, and then since you didn't specify, usually it's possible to specify what you are looking for. If you know it, if you know exactly what you are looking for, you can type a keyword. Somewhere here at the top right corner, there is a keyword. You can see in front of keyword you have empty space. You type your variable of interest, or what you want to look. For instance, if it's surface runoff, you type surface runoff. If it's a ground recharge, you put a ground recharge, whatever. Or if it's precipitation, type precipitation, and then click on search, and then you'll get a list of possible data that contains what you are looking for, because there are different data providers that provide the same thing. So you'll see a lot of options, and from there you have to make a choice. You have to make a choice, and you have to click on in front of what your choice. This is just a kind of menu, list of options, and you have to make a wise decision. Under this list, for instance, since I didn't choose exact variable, there are different options for me to pick from this. And if you move further to the right, it shows you the unit in which the data is given. For instance, the first one is downward long wave radiation flux. Yeah. By the way, is it clear? Because this is a very crowded slide. I don't know whether you can see what appears on the screen. Do you see them? The list of data.
It's not clear.
It's not very clear, right?
But if you log into the website, you can access
Yeah, definitely. I mean, it's for you to go back after this lecture. You can go back, register. You go in, then you can get them. And if you have some difficulty of using them, you go back to this presentation and try to zoom out and see what is there. So there are units of the data in the first column on the left side, on the right side, sorry, of your screen, and then source of the data, who provides the data, is provided under the second column, and then the temporal resolution, temporal resolution. It could be daily, monthly, it could be even hourly in some cases. And then spatial resolution is given in degree here, and then the time period which is covered by this data is given in the fifth column on the right, and then end date of the data, and so on. Vertical slice, this is when you have a data, not only surface observation, but also it's possible to have observation at, let's say, 10 meters above the surface, 5 meters above the surface, or you can go even up higher, 10 meters, 20 meters, 20 kilometers, sorry, and then up to 100 meters, because this is upper atmospheric observation. It's possible. You can do that through balloon, through radio sonde, through aircraft. You can make measurement at different atmospheric levels. So in that kind of case, you will have also vertical slice, vertical information. How far the data is spaced from each other vertically. That's what you get from this kind of slide. So once you click on one of these data and then you want to proceed to analysis, what you'll see is the screen on the next slide. So you see now, I just cut small portion of the screen. That's why now it's clearer, I think. What appears is just a small portion of the slide before, but in a different mode. Now, what I did here was, once I choose, I just press here at the bottom right, float data, which is shown by green color here, yeah? Green color here. Float data. Once I press that one, the next screen will appear here, which is this one. So depending on the kind of data you have chosen, it will take a while. You know, the data could be very large. So what it tried to do is first access the data, and then analyze the data in the way you have requested, and that will take some time. So it's processed on the other side of on the data server actually, and then sent appear on your screen. So there is a computational issue. There is also data transfer, the internet issue. So that will take some time. That's why you see workflow. If it's completed, then workflow is completed, and then visualization is pending. So this blue bar should finish up to this point, should cover the whole white area. And then once that is done, then you'll see a screen on the, instead of this screen, you'll see another screen which appears like this one. So this is a plot, for instance, temporal average of total evapotranspiration monthly. And this is obtained from this model. It's a reanalysis, not a model. Reanalysis, it has observation, it has also models. So you see a continuous map of total evapotranspiration. I have showed you yesterday a lot of things about this. And here you have on the right, top right corner, you have options, and then you have a download icon. There are two icons here at the right top corner, options and download. If you are satisfied with this kind of map, and you think this is good for you to even to present in a paper or for a presentation, you can download it directly. If you feel that you want to change a few things, you go to option, Even you can change the kind of color that you want to use. It is from red to something like a blue, but you can change the color choices. There are many color choice options when you enter here and modify. Even here, the title here is a lengthy title. Every information is given on this map, as you can see at the top of the figure. But sometimes this information may not be necessary. Yeah? So we want to shorten to something short and understandable, so you can edit it, you can remove it as if you will, if you wish. So there is a possibility to modify the map. Okay. So that is it regarding the exercise. There are two data platforms. One is Giovanni, which I showed you now. It's it has a lot of data compared to KNMI Explorer. There are two data platforms that I provided with that information. Yeah. This one is a bit. It's not very tough. It can be used efficiently, but there are steps that you have to follow. The other one is more friendly, but limited in the scope of what you get out of it. Yeah, and then the number of data that is available in the other one is also very much limited. Here you have observation, you have models, you have models and observation combined, which you call it the reanalysis. So this platform can be used even for research, not just for understanding what's going on, but you can even do some kind of research related to your work without really do some analysis using GIS. You don't have to even do that, or using some writing program to plot this kind of graphs may take you time. So this is a very simplified tool that you can exploit even for your research. So with that, I will proceed to my talk where I stopped yesterday. But before that, maybe I'll give you a few minutes if you have a question. I can go back to the slide, explain.
Question.
There is a question?
Yes.
Yeah. Go ahead.
My background is computer science, so I have come across this under the slide where you have information for the exercises, water availability, quality, and vegetation conditions. So under that table where you are showing product, satellite sensors, spatial resolution. So under the column spatial resolution, I've seen that you have the measurements are represented by 3 different units. There is meters, degrees, and also square meters. So I do not know what it really means in terms of the spatial resolution and in relation to the units themselves. Yeah, so I just want you to explain.
Yeah. I think you are talking about the top right corner of your screen, right?
Yes. In fact, the first table, which shows it has 5 columns: product, satellite sensors, spatial resolution. Then the next one is not clear. Then the last one is frequency.
Yes. Yeah. In terms of the spatial resolution, you see 2 resolution, right?
Yeah. So I've seen 3 units being used. There is meters, then degrees, and then square meters.
I don't see square meter. In the first one, a kilometer squared. If you are looking at grace, is it grace? Can it be specific?
Yeah, so it's grace where you have 150,000.
Exactly. Yeah. No, the idea is here. Basically, these are two satellites. One is for the first version, which runs from 2002 up to 2017. The other one is a more refined one, 0.5 degrees, about 50 kilometers. Okay, 50 by 50 kilometer resolution means basically we are talking about the pixel on the ground. The pixel on the ground will have 0.5 degree by 0.5 degree. If you translate that to area, it's going to be 50 times 50, which is around 200 something, right? Yes. 50 times 50 is going to be around 2,500 kilometers square. So the latest version, the GRACE FO, has much higher resolution in terms of coverage. They are the same, basically. You could put the first GRACE also in terms of just one side of the pixel. For instance, this could be something more than a degree or 2 degree. Yeah, you just have to find out the scale of this one. So basically, the units are the same. Degree is the same as kilometer, but the lower one also only give you one side of the pixel, maybe the east-west side. Because of the east-west side, this is a square pixel, so you don't have to repeat the other one. So you could say 0.5 by 0.5 degree is still acceptable, but there is no problem in this. Both are referring to this pixel size, the pixel size. Let me put that way. Yeah, exactly.
So what it means is the pixel size can be represented by the amount of degrees or amount of meters.
Yeah, it's possible. You can convert them. These are all convertible. You know, 1 degree is around 110 kilometers, right? Yeah, you can give, sometimes if the pixel size is big, you prefer degree, because if you use a degree, you give a small number instead of saying 110 kilometer resolution. Yeah, you can also put it in kilometers. It doesn't matter. Kilometer can be converted to also meters. So these are units of length anyway. Units of length, it doesn't matter. And if it's just one length, it just gives you the one side of the pixel, the square pixel. If it is an area, it gives you the area covered by the pixel. So it's the same thing. We are saying the same thing. There is no difference in this case. But I think the other issue here, I would say maybe not clear, is 500 meters, let's say 5 kilometers. There are two resolutions. So you could have also asked those questions. But the two resolutions are, from models, there are several products. Some are very refined resolution. Even 250 meter resolution is there. You can see here, down here, for river wheels. Some are coarse resolution because of the kind of processing is involved. You cannot go, let's say, for 5 kilometers. You may not go below 5 kilometers because of the processing techniques. Some are processing techniques sophisticated. You can resolve all the way to a few meters. So even for the same instrument, you could have a product with different resolution depending on the accuracy. Are you together? Yeah. Do you have a follow-up questions?
I think there are no other questions, Prof.
Okay. I think that it would have been the best if you have tried, because definitely you'd have a lot of questions if you have tried, because unfortunately I gave you very lately the information. Maybe you didn't have time to create and try to explore the questions that some of the exercises that I gave to you. But I'm still open for discussion even after this lecture. You can send me email asking me questions. We can even arrange a sort of Zoom meeting one-to-one where you can show me your screen and we can sort out, I can help you in that direction, yeah? But just go inside, try to explore, and definitely get a lot of information, and you'll have a lot of questions that arise from practical use of the platform, okay? All right, let me move. So yesterday we covered this aspect. As we have seen, climate change affects not only the mean climate, yeah, like the trend, but it also affects the extreme part of the time series. If it's temperature, both tails of the distribution, the lower tail and the highest tail of the distribution is affected. And if it's precipitation, the same occurs. The lower tail as well as the upper tail of the distribution is affected. In short, we said that climate change affects every part of the time series, not only the mean, but also the extreme part. Because this extreme part, we are focusing on the extreme part because they have more impact when it comes to hazard. Otherwise, you can talk about change in temperature, rainfall, and other variables over the whole time series. So that was the understanding. And now today we'll continue from here, talking about the different extremes, the terminology that is used. We usually refer to severe events. And these are events that create large loss in terms of lives, for instance, financial capital, environmental quality, example, loss of a species. So we characterize as severe events. Severity you can measure using risk, which depends, as I said yesterday, probability of the event or the hazard itself, exposure to the hazard, and the vulnerability, which is how much damage will follow when someone hit by the event, for instance. So this information will be used to characterize severe events. Rare events in this category, rare event, low probability of occurrence, happens maybe once in 1,000 years. It depends, even an event that happens once in 100 years, we call it rare events if it's the only ones. Extreme events that have extreme value or certain important metrical value. And in this category, we talk about flood, high wind speed, for instance, cyclones, heat waves. These are coming under extreme event. High impact event, mostly in terms of economy. Here we can look at drought, heat waves, and so on. So these are the terminologies that people use when they talk about extreme event. Extreme event is basically a multidimensional. That means you can characterize it in terms of different metrics, in terms of different aspects or properties. So that's why we say multidimensional. For instance, rate probability per unit time of occurrence is one aspect with which you can characterize an extreme event. Magnitude, the intensity, not only the frequency of occurrence, but the magnitude, because the extreme events have different magnitude, as we have seen. So you can use that also as one additional parameter is additional dimension. Rate is one dimension. If you add magnitude, it's going to be the second dimension or another way of characterizing the extreme climate event. Temporal duration, once the event happens, how long it's going to stay there. Yeah? Is it a one-day event? Is it a two-day event? Is it, let's say, like a drought? Is it a one-year drought, two-year drought, prolonged drought? So that also gives you additional information about the characteristics of extremity, because they are complex. We have to use different metrics or different properties to characterize them. That's why we call them, these are multidimensional events. Spatial scale, is it highly localized or is it a widespread type of event? That's also important. You know, if it's a very localized one, it's a small scale. It's a large scale, let's say continental scale or a global scale, is a very large event. So that can also be used to distinguish one extreme event from the other. So these are a matrix, basically a matrix by which we can characterize them. So we see this is a fourth dimension. And of course, all of these are dependent on each other. You know, if you want to really provide probabilistic forecast of an extreme event, you need to ask what is the probability of an extreme event or climate event coming, let's say, every 10 years with a magnitude less than this one, with a duration of lasting for this much time, with an area covering this much, and so on. So all this has to come into consideration when we define, even try to give a kind of probabilistic expectation. So in general, we can characterize them in this multidimensional aspect. So for instance, you can see rapidity, severity, rarity is how you classify this as a table. Rapidity, rare non-severe chronic event like cold spell in Sahara, rare non-severe acute event, hurricane over South Atlantic Ocean. This is one example. Rare severe chronic event. I'm just looking at the bottom panel, the bottom boxes. Drought in India, for example. Rare severe acute event. Yeah, it is given, for instance, in England we have hurricane, and then you see rare and severe event, rare non-severe event. That's how you classify them. So there are different ways of characterizing an extreme event, and in fact, that makes it very challenging because the extreme event can vary as function of rate, as function of its magnitude, as function of its temporal duration, and timing of occurrence. Timing. Is it a winter event? Is it a summer event? Is it a spring event? That's important. We can go even beyond that one. Is it a January event? Is it, let's say, a July event? You know, you can really ask those questions, and you can use this information to really uniquely characterize them from other extreme events. If you give a value for all of these, then you are able to define the extreme event uniquely from other all extreme events. If you are not able to do that, definitely there is an ambiguity to distinguish one extreme event from the other, because they are different in terms of rate of occurrence, they are different in terms of intensity, they are different in terms of lifetime duration, how long they stay once they appear, and in terms of time for preference of occurrence. Yeah, some even, for instance, heat waves are usually expected during summer, right? Naturally, when you are talking heat wave. Yeah, cold wave, basically the timing is in winter, so they don't occur at any time. Timing is important, but how long they last when they occur is another question that you have to ask, because some can last very long. Some are very short, and the impact is also mild, the impact of these extreme events. So that's why we say climate extremes are multidimensional and as such have multi-attributes that can be used to characterize them. And they are challenging because of this reason. These are some of the lists that probably you know, at least from news. Not all of them are appearing in Africa. Tropical cyclones are definitely. Hurricanes and tropical cyclones are the same. It's only the location. Hurricanes are usually they are also tropical cyclones, but occur in America. In America, extra tropical cyclones, from the name itself, these are not tropical. They are mostly appearing in mid-latitude over Europe. Yeah, convective phenomena such as tornadoes. Yeah, also occurring in most part of the ocean. Water spout, severe thunderstorm. It happens everywhere, even in Botswana, in Namibia. Yeah. If you can bring this into this also. Dust storms, yeah, dust storms are part of the climate extremes nowadays, because there has to be a wind, strong wind that triggers the dust storm. So this usually lead to extreme local winds. Most of these tropical cyclone, hurricane, extratropical cyclones, convective events like tornado, waterspouts, severe thunderstorms, they are all extreme. They may lead to extreme local wind speed. The impact comes from there. And extreme amount of precipitation. Extreme amount of precipitation. I will talk about this. I have an example from this region, but you have to wait for a few minutes before we reach there. Some example of recent extreme event which is related with cyclones, for instance. Mesoscale phenomena, such as mesoscale convective systems. Usually the size of these systems are only 100 kilometer wide, very, very localized. It's not a large scale. But for tropical cyclones, yeah, it's widespread, you know. Cyclones happening over Mozambique area could have an impact all the way to Botswana and also Namibia in some cases, right? At least you'll get an impact, a leftover type of impact, highly weakened, but you can feel it, the impact. We get, if there is a cyclone, storms over Mozambique and Botswana, we get it. And I think part of Namibia will also get some signal, but at a very reduced intensity. Floods of rivers, lakes, coasts due to severe weather condition, can happen, such as river floods, flash floods. Droughts is very common in this region. Heat waves, periods of exceptionally warm temperature, which can even impact human health. You know, people have died actually in this region during the recent heat waves. I'll talk about it later on. Duration is important component which determines the impact, not only intensity. Duration is important. So fog itself is another extreme event. You know, fog will reduce visibility, will lead to major aviation and road transport interruptions, and the impact in terms of economy. In some cases, could also lead to deaths, life loss. You know, there are cases where aircraft crashed because of local extreme events such as fogs in the past. Nowadays, aircrafts, bigger aircraft, I'm not talking about small aircraft, moving people between, let's say, from South Africa to Botswana or Namibia. I'm talking about big aircraft, regional aircraft. Nowadays they use GPS even for landing, yeah, for landing, and it doesn't depend on visibility at all. You know, GPS can work at any time of the day, during any time of weather phenomena. It's a radio wave, and a radio wave doesn't interact with a lot of the atmospheric processes, clouds, fogs, doesn't interrupt the radio wave signal, the GPS signal that's at least used for navigation purposes. But in the past, there were a lot of accidents as a result of extreme low visibility due to fog. The risk of flooding is a global concern, particularly due to climate change. Coastal and delta regions are particularly vulnerable. We have a delta here between Namibia and Botswana. The risk of, through extreme precipitation, flooding through extreme precipitation is a concern nowadays. In the polar region, yeah, such as Sweden, Norway, glacial melt could lead to flooding, yeah, river flows, because most of the ice melt will flow to rivers. So these extreme events are affecting every region. We may not get glacial melt in African region, in tropical region in general, but we are definitely going to get extreme precipitation event. Drought is also, as I said, is one of extreme events. So it's a multidimensional, and usually we have drought of different classes, depending on the duration. So we refer to Mesoka droughts. It's basically a prolonged period of low or insufficient precipitation. Usually, Mesoka droughts is about a month. About a month period, we'll describe it. Mesoka drought. So for agriculture, is also a serious issue. Actually, even one month's precipitation loss could affect agricultural productivity. But we have also agricultural droughts, not only affecting just rainfall, but also affects the soil moisture, because sometimes even with mild or low precipitation, you can still carry on your agricultural activity, and you may get some production with, of course, low yield, provided that there is enough moisture in the soil. So if the drought is so severe, there is no rainfall for maybe a little more time, up to 3 months, that could start also affecting the soil moisture. So once the soil moisture is affected, agricultural productivity will basically go to zero. So in that case, we define agricultural drought. Hydrological drought is actually not just about rainfall, but when we have reduction in flow in the rivers and also in the reservoirs, even the reduced groundwater levels is what we refer to hydrological drought. And the fourth one is includes the impact component of the drought. It's a socio-economic drought, yeah, socio-economic drought, and it can go well with meteorological, hydrological, and agricultural drought. And if you have impact on the supply and demand of economic goods, yeah, along with one of these, along with meteorological or hydrological or agricultural drought, then we call this as socio-economic drought. So still you can talk about other aspects of drought, yeah, other aspect of drought, and define new category of drought is possible, depending on what you want to see. Because these drought types are defined by indexes. How do you distinguish one drought from the other? It depends on index. Usually for drought, we use standardized precipitation index. It's only built from precipitation. And we also have standardized precipitation evapotranspiration index, which take into account the water balance and also the impact of temperature into drought. So we have different classes of drought based on those indexes. So basically, we have different extreme events. Floods and droughts are just one of them. One of them with a very high economic impact, socio-economic impact. But there are also other extremes that we are going to discuss. But before that, I just want to really remind you about the recent extreme events. Yeah, the recent extremist event. Here is a map which is published in the American Meteorological Bulletin, BAMAS, Bulletin of American Meteorological Society. It is about the Southern Africa. South Africa is left out because the report for South Africa is separately prepared. It was not intentional. And you can see seasonal rainfall in 2050 over South Africa as a percentage of 1981 to 2010. So 1981 to 2010 was a base period, was a reference period. So we are comparing the 2050 rainfall, seasonal rainfall, with the corresponding reference period seasonal rainfall, mean rainfall. So we have 4 seasons here: DJF, which is basically the summer here, March, April, May, June, July, August, which is a winter, and SON. And clearly, the color bar shows from brown to green. As you go to green, there is excess. As you move further towards more brown color, you get a deficit. So basically, you can see Namibia during DJF and part of Botswana, there have been the mean precipitation, the mean rainfall was actually below 30% of the normal. During this 2050, we received only 30% of the normal. So there was a loss of about 30% of the normal rainfall during 2050 over this area. And of course, in MAM, you have some excess, but in winter, obviously, again, it's a deficit. In SON, I remember September, October, November, actually in this region from October to February is where you get a lot of rain. So SON is also supposed to be a rainy period. Again, here, actually the deficit goes well into below 20%. So the rainfall received in 2050 was below 2% of the rainfall, the normal rainfall for the period 1981 to 2010. So this has a very severe impact. This work is actually published. We reported on the state of climate in 2005. It's a regular bulletin which publishes state of climate globally. Fortunately, at that point, I was representing both Eastern Africa and Southern Africa to report on the state of climate, and this result is reported in this bulletin. You could even go there and look at the detailed description here. As you can see in the red color here, this is a reference, and the DOI number where you can click and print it, because these are free publication. And the same year we had a heat wave, as you can see, a heat wave during DGF, and clearly during SON. And what you see here is heat wave is basically defined as heat wave duration index, HWDI, a maximum period of 5 consecutive days with maximum temperature 5 degrees above the mean of 1981, 2010 daily normal maximum temperature. Remember, we are not talking about the mean temperature. We are talking about the maximum temperature. When talk about heat wave, it's all related with maximum temperature. As a meteorologist, I'll tell you that we get every day minimum and maximum temperature. Maximum temperature is during daytime, and minimum temperature is during nighttime. So this physically is supposed to coincide with the location of the sun. For instance, the maximum temperature should have been just noon when the sun is overhead at a particular location. But there is a delay of time. First, the atmosphere should absorb, and then it start to build up heat. So usually the maximum temperature during day appears 2 to 3 hours after noontime. So it's around 3 or between 2 to 3 p.m. in the afternoon. That's when you get the maximum temperature. The minimum temperature should have been, in principle, just at the mid of the night, which is 0 a.m. But there is also a delay there. The minimum, the coldest time, if you just try to follow, you can check if you are awake in the night. The time where you feel cold and where you feel more blanket is around 2 to 3 a.m. So this is just additional information. Otherwise, I'm talking about extreme events. So extreme heat wave refers to the temperature around 2 to 3 p.m. in the afternoon. So this shows days where the maximum temperature exceeds the mean maximum normal temperature by 5 degrees. Yeah, at least for 5 consecutive days. It can be 5 degrees or more for 1 or 2 days, but in that case we cannot classify as a heat wave. Yeah, to be considered as a heat wave, that maximum temperature, which is more than the normal maximum temperature of the reference year, should last at least for 5 consecutive days. It has to be consecutive because it can happen every other day. Cannot be even classified as heat wave because the impact is going to be low. If there is continuous heat for a period more than 5 days, that is when we consider this as heat wave. So clearly you see that there was a heat wave during this period here, during September, October, November period, and during DGF. And actually, I'm not sure, perhaps it's from South Africa, it's not from Botswana or from Zambia or Zimbabwe. There was a case of this that was reported. Of course, I think if you click on this publication, you'll find the information. I forgot now to remember exactly where it was. There was a fatality related with this heat wave. In 2007, as we said earlier, the extreme climate events, they are extreme, but they are also reappearing very frequently. So we are having extreme events year after year, and the drought was in 2015. The heat wave was also in 2015. But in 2017, and later on I'll show you in 2018, we start having excess rainfall as a result of cyclone. For instance, there was a cyclone Carlos, which was active from 3 to 10 February 2017. And then there is a cyclone Diano. It was occurred on February 30, actually, just a few days after the cyclone Carlos. And they resulted in a very huge rainfall over southern Mozambique, southern Zimbabwe, as you can see, as shown by this very green means the amount of rainfall here is actually 200% of the normal, 200% of the normal, above normal, 200% above normal. So even in Botswana, we have heavy daily rainfall as a result of cyclone Diano. I don't know whether I pronounce it correctly. And other in this case, it was in fact a good one because in 2015, 2016, as you have seen, Gaborone Dam was almost empty. Yeah? You are not allowed to wash car using pipe water, yeah, because of the severity of the problem. And I remember there is also a serious issue in Cape Town, I think, in Southern Africa. Water was rationed, and there was a prediction that they were going to run out of fresh water in just few days. Yeah, but I think they survived anyway, that event. So Gaborone Dam, which was almost empty in 2015, 2016, was filled up by this huge rainfall. You know, that was a drought that persisted for almost 2 years, making the whole dam empty, basically empty, could not provide any water. But in just a few days, event, the dam was filled. So there is a lot of torrential rainfall, very excessive rainfall that was really flown into the region because of this extreme tropical cycle. So you can see rainfall amount, daily rainfall amount from 120 to 192 millimeters, yeah? Spilling over the dams during this period. Yeah. This is for 2018. There was no actually any tropical storm. It's just a rainfall, extreme rainfall, convective rainfall that led to this kind of high precipitation in the region. So you can clearly see that the region is also experiencing more frequent extreme events, which has led to a lot of damage also. For instance, in South Africa, excessive damage to roads and electricity network has occurred, yeah, because of this excessive rainfall in 2018. Yeah, now that was just kind of information for you that this extreme climate events is happening in the region. You can witness them. Apart from that, because of this, the occurrence of increase in frequency of extreme events, we initiated research to understand whether there is a trend. Is this happening now, or is this is something that is happening in the past, but we are not able to notice because the impact was not that severe? So to find out that, what we did was we went all the way up to 1981, try to look at extreme events related with rainfall and temperature. So what you see on this slide is, for instance, the panel A at the top left and panel B at the top right. represented an index, number of days during December, January, February season with precipitation exceeding 10 millimeters. So this is a number of days during the 3-month period throughout, of course, from 1981 up to 2022. So clearly here, what you see is there's not much rainfall in much of South Africa, shown by blue. You can see only about 6 days, only about 6 days in a month, in a season actually, in a season, get rainfall of this kind, 10 millimeter and above. Botswana, basically almost the whole country except areas close to Kasane and bordering Namibia and so on, gets only about 6 days of rainfall with maximum rainfall exceeding 10 millimeter. And Namibia is the same, it's not exceptional. Namibia basically the same as Botswana, except areas bordering Angola. It gets only about only 6 days from 90 days or so gets a rainfall of 10 millimeter and above. Whereas the northern part of SADC, as you can see here, shown in red and yellow color, you can see yellow is somewhere between 24 to 30 days, and the orange color is from 30 days to about 36 days. So within a month, you can see there is a lot of rainfall with this kind of intensity. For the northern half of the SADC region, Zambia, Zimbabwe partly, and then Mozambique, this kind of 10 millimeter rainfall is very frequent, at least from 3 months, 1 month can get a rainfall that exceeds 10 millimeter for the last 14 years, for the last 42 years, yeah, 42 years. And is there any trend? Is this maximum rainfall exceeding 10 millimeter? Is it increasing with time, or is it decreasing with time? When you look at this, nothing has, well, most of the Southern Africa region is shown by white. White means there is no significant trend. Wherever you see color, there is some significant trend. And what you see here, for instance, in Namibia, only a few isolated places close to the coast has some change, which shows actually there is a further decrease in the number of days with rainfall greater than 10 millimeter. Yeah, even historically, the mean number of days with rainfall greater than 10 millimeter is about 6. But even these 6 days are decreasing now. That's what you see from Namibia along the coastal areas. And for Botswana, actually, it's increasing. It's increasing over. I think this is area northeast part, and then also around the Kalahari areas. There is some increase, which is over the last 42 years. There is an increase of at least one more day per decade. 1 more day per decade. 1 more day per 10 years. So what that means is that Botswana in these areas is now getting about 8 to 9 days of rainfall greater than 10 millimeter. greater than 10 millimeters. So you can look at Angola. Angola also shows some increase in the number of heavy rains. 10 millimeters is considered as heavy rains. And it's increasing with time. From 1981, after 2 days, showing some increase in some parts of Angola, but the rest are normal. I think it's something good because either positive or decrease, both are not required because they have high impact on the economy. The other parameter that we looked at historically, basically what this shows is in terms of the rainfall distribution, heavy rainfall distribution, the change is not that significant. The majority of the SADC region is close to normal. Only a few isolated places are showing some change as far as the first two panels are concerned. The first two panels are concerned. And the second one is C and D, panel C and D in your figure. I think you can see them. Here, this is a maximum 5-day mean rainfall in millimeter, actually, in this case. You can see it ranges from a few millimeter to 230 millimeter, 230 millimeter. Your maximum 5-day rainfall, as you can see, Mozambique is a place where you experience that kind of heavy rainfall within 5 days. And you can also go to here, maximum 10-day rainfall of 312 millimeter is observed over the same area, actually, over the same area. Sorry. So I think I'll give you a break at this point. It's almost 10:30. So we'll be back in 10 minutes. Thank you.
Thank you, Prof.
Thank you.
Switch. Take 10 minutes break.
So shall I continue?
Yes, please, we can continue.
All right. Let's continue. Yeah, I think we are all okay now. Yeah, I've discussed the three index. There are so many index out there that describes the extreme, let's say, rainfall variability. These three are just a few of the many other indexes to describe extreme conditions. What I didn't discuss is, for instance, in panel CD and EF, there is a corresponding trend in these indexes as the temporal evolution. When it comes to 5-day maximum day rainfall, actually it shows a decrease in over the northern half of the SADC region, and an increase over part of north eastern Botswana, and also part of Zimbabwe and Mozambique. Little isolated place, not substantial. For 10-day, the trend is the same. It's decreasing. It's decreasing, and well, departure from normality is not what is favored, but this is happening because of climate change. The other index from many of the index that is used to describe rainfall is the dry day persistence. You can have dry day persistence for the season. You can have annual dry day persistence. Basically, what it means is the number of continuous dry days within the season to the total number of dry days. Yeah. Right. So in this case, if you look at the panel A, it ranges from 0 to 0.96. Normally, it should be from 0 to 1. 1 means the whole season is dry continuously. And as you go down, then you have days, only few days which are dry continuously. So based on this, for instance, for December, January, February period, the northern part is wet because it has a dry day persistence less than 0.35, less than half of the, if it's 0.5, half of the season out of 90 days in a season, about 45 days are continuously dry. That's what it means. So here, that's not the case over the northern part, but naturally, as you can see, it also can be perfectly used for aridity. You can see Southern Africa, western part of South Africa, and the western part of Namibia. They are really almost dry throughout the season. That's what the rate shows, 0.96, only a few days of rainfall. This is part of the Kalahari, anyway. And so you can see not only the extreme situations, that's how you describe the change in the rainfall in terms of whether you are having continuous dry, continuous wet, and so on. This one here at the bottom is for another season from October, November, March, because this again a rainy season for the region, and the pattern is more or less the same. You can see before this season, actually, this area which is red by color is continuously dry during September, October, November period from historical data. In terms of temporal evolution, the trend from 1981 all the way to now, what you see here is a decrease. That means the northern part, the blue one over the northern half of Southern Africa, actually it covers only a small portion of Angola, and most of it is within Congo area. You can see that there is a decrease in the continuous dry days. So the dry day persistent is decreasing. The blue shows negative. And the color, yellow color here, shows that part of coastal areas of Mozambique, including Southern Africa's eastern coast, is slightly getting drier because you see a yellow and green, which is a little above zero. Of course, this is not a very significant persistent. It's very small amount of. When it comes to temperature, so far we have looked only about rainfall extremes. Yeah, all those indexes are basically about rainfall extremes. Here we have heat wave duration as one extreme that characterizes temperature extreme, and then annual temperature range is another parameter that you can use to describe temperature extreme. And then at the bottom, average mean temperature change can be used as one parameter to describe change in temperature due to climate change. So basically, as far as heat waves is concerned, we are looking at the summer heat waves, and you can clearly see most of the heat wave with a longer duration is focused in this area, with a red color, and the rest with the blue. You can see it's not that long duration. And in terms of trend, basically the central part of SADC that covers Botswana, Zimbabwe, Zambia, actually around the this river area, Kasane and Zambezi River area. Basically, what you see here is there is a decrease in the heat waves, the decrease in the heat waves when you look at the historical time series from 1981 up to now. And the only place where you expect some increase in heat wave is the south eastern part of South Africa. You can see a red color here. There is an increase in the long wave, the heat wave duration for this area. Looking at the middle row of your screen, we are looking at interannual temperature range, mean interannual temperature range, and what you see here is the mean temperature. Usually, the Southern Africa part and part of Namibia is warmer, and then you see yellow color. Then I mean the range is high. What it means is it's logical also. It's not necessarily part of climate change. It's part of the normal climatology. You know, as we go further south, in tropics we don't see big temperature difference, interannual temperature difference between maximum and minimum. Yeah, that's what it means. Interannual temperature difference between minimum and maximum. The difference is very high as we approach the polar region, because those areas get the sun only for very limited time of the year, whereas the sun is always residing along the equatorial region. So because of this, when the sun is close to the polar region, it is extremely hot. When the sun is far away, the polar region are actually in the dark. You know, the day length could be only 4 to 5, 6 hours. In Norway, for instance, yeah. In the summer, the day length, you can walk, just walk without any electricity, any street light. You know, somewhere around 9 p.m. it still look like a day. Yeah, because of this difference. So what you see here is exactly that reflection. So farther south, the difference in interannual temperature range between maximum and minimum is high, because the southern part around Cape Town gets extremely cold during winter, extremely warm during summer. That's what you see. And the difference could go up to 30 degrees centigrade difference. That means the winter could be below 0 degrees centigrade. The summer could be close to 40, 45 degrees centigrade. That's what it means when you see this kind of temperature range. In the middle, you see yellow color. That temperature range is between 20 to 23 degrees centigrade. So a lot of much of Botswana, much of northern half of Namibia, and northeastern half of South Africa is under this category. If you move further north, actually the difference between winter and summer temperature is getting low. So what is interesting here is usually climate change is affecting the minimum temperature more than the maximum temperature. That is what we have found from doing science, and that means the colder temperature is becoming warmer. That's what we have discussed yesterday, and the warmer will be even more warm. But the rate at which the two are changing are different. The colder temperature is getting warmer much faster than the warmer temperature are going to extreme warm. So as a result, you'll see that the difference between minimum and maximum is decreasing. And if you look at the interannual temperature range and how this evolves over time, basically, you see under panel D here, interannual temperature trend, and it's shown by the color blue. Blue means negative. If you look at in the color, blue is negative. So there is a decrease. This difference between minimum and the maximum temperature is decreasing over this region. So the distinction between cold and warm period is decreasing this time. That means the minimum temperature is becoming warmer, while at the same time the warmer temperature is becoming even further warmer, but not at the same rate. So the warmer temperature is waiting for the cold temperature to catch up. As a result, what you see here is the trend is rather of the difference, the interannual temperature range is decreasing. It shows us that the minimum temperature is warming at faster rate than the maximum temperature over most of the central part of the SADC region. That includes Zimbabwe, Zambia, Angola, and so on. If the other part where you see just white, there is no significant trend. It remains the same. That's what it means. There is no. That means basically the climate change is not affecting those areas in terms of interannual temperature change, where you see completely white, but the color ones are showing some change. Of course, you can see some yellow color, which is positive. This is in the Congo area. Actually, the difference between minimum and the maximum is widening in this case. It's the opposite of what's happening. That is not what we expect normally for when we talk about climate change, but it's happening in the opposite direction. In fact, it's true also for small isolated place in Southern Africa. So, Southern Africa, where it's towards the western side, southwestern side of South Africa, you see also an orange color, where the difference between minimum temperature and maximum annual temperature is actually increasing. They are widening. They are going in the opposite direction. That's what it shows. Now we look at the mean temperature. The mean temperature again. You can see the warmest places are in along the border of Botswana, and Namibia and South Africa. You can see that this red color here. In terms of mean temperature, throughout the years, this area has remained warmer than general normal, warmer compared to the rest of Africa, the rest of Southern Africa. And then along the Mozambique coast, this is also a place where you see a lot of warm temperature, mean warm temperature. But what happened due to climate change to this temperature pattern? You can see the trend is shown from here, from minus 0.57 blue color to red here, 0.87. So temperature increase, basically the red means there is a temperature increase, and blue means there is temperature decrease. So the mean temperature is decreasing over Botswana, and also over Zambia. In fact, that includes also some isolated periods in Zimbabwe and area between Zimbabwe and Zambia, and some areas along the coastal areas of Mozambique is getting also slightly warmer. And this area here, in terms of mean temperature, is getting warmer. It's getting warmer in the Southern Africa region. So the trend is a mixed signal. Some places are getting warmer, some places are getting colder because of climate change. So this is at least as far as the data covering the period from 1981 up to current is concerned. Yeah, and another issue is when you look at these extreme cases, can I take a call? It's very urgent. Sorry.
It's okay, Prof.
Sorry for that. It is an urgent call. So let's continue here. Now we have seen some example. Actually, what we have seen earlier in terms of describing extreme climate events, basically temperature and rainfall. These are the most important parameter, of course. I don't mean that others are not significant. There are change in other parameters. So one has also look at evaporation, what's happening. If you want, you can do the same thing, evapotranspiration, which is affected by both land use, land cover change, as well as climate. You can look at different component of the water balance, as you have seen earlier. But I'm just presenting these two cases for the Southern Africa because this research was initiated by the fact that there was some increase in frequency of extreme events in the last few years. That's why this research was initiated. Otherwise, there are so many other indexes that you can analyze to really get what's happening on the ground in the region. So usually, you know, as one of you have raised yesterday, climate change is debatable in some corners. Some argue that it's just part of the natural process and try to explain it what they see with some kind of evidence. But the point is, which evidence is more outweighing when we compare the two extreme arguments or views on climate change. So it's important we should also look at INSO. Whether INSO is connected with some of these impacts from the region. We know INSO, La Nina, and stuff, and this the warm and the have different opposite signal. So La Nina during La Nina usually is for Africa, most Africans actually, including South Africa, generally the cold phase of INSO, which is La Nina, is providing excess rainfall to the region, whereas El Nino is the one which is associated usually with drought. But we have to be careful because even in South Africa, the response to the different phases of INSO is different. The warm phase of INSO is El Nino. The cold phase is La Nina. And they have different impact in terms of rainfall and temperature in the region. Here is what we see on continuous. What is the impact of these phases on the continuous wet days and also on dry day persistence? On the top panel, the dry day persistence. If you want to see what happens during El Nino, one phase of INSO, all you need to do is identify those years that have El Nino occurrence and do the composite or the average of those years for dry day persistence, for instance, here, and for continuous wet days also here. And there is also PNL90, another index that describes wetness. And you can also do greater means the basically El Nino, less. The less symbol here shows La Nina. And then if you take a difference between these two, if you subtract La Nina period, the La Nina composite from the El Nino composite, you get this one here. This is a difference, which is represented by minus sign here. So clearly what you see is the dry day persistence has a different effect, during El Nino and La Nina. If the whole region behaves exactly the same way during El Nino and also exactly the same way during La Nina, the difference between the two should show the same color, either red or blue. But what you see here is that the northern part of the SADC region, which includes much of Angola, and then Congo and part of Zambia, and then part of Mozambique, turns blue. What it means is precipitation, dry day persistent during La Nina is greater than during El Nino, which is opposite to what we know actually, because El Nino is associated with drought, low rainfall, and La Nina is associated with good conditions, excess rainfall, flooding, and so on in the region. But what you see here is over this region, Angola, part of southern DRC, and then Zambia, part of northern Mozambique, is that you have the opposite effect. So the effect is different. So that means number of days, continuously dry days, is less during El Nino over these areas, over the northern part of SADC region. That means contrary to what we know, El Nino is a dry period, La Nina is a wet period in the region. But here you can see clearly that northern part of Angola, northern part of Zambia and Mozambique get actually good rainfall. At least the days are wetter during this period as compared to La Nina period. And then the the region except again part of northeastern part of South Africa. The rest is either completely red or something light red, which shows that basically La Nina is the opposite condition. So so the response of the region to the different phases of ENSO are basically different. And looking at continuous wet dates, you see exactly again blue in the central part where you have dark red here, dark red, strong red color. If you look at the middle row, and here again blue is negative. That means La Nina is, in this case, is better over this area in terms of continuous wet dates. Yeah. So there is again different response to different phases of the ENSO. So you cannot generalize that La Nina is a dry period, and Lino is a dry period, La Nina is a wet period. Yeah, the response depends on the region for various reasons. Of course, one has to explore why they are respond differently. Is it because of the local factors such as vegetation cover, because of water body available in the region, because of the topography? There are many factors that play into the climate, apart from the sea surface temperature. ENSO is about change in the sea surface temperature in the Pacific, right? In the Pacific, and you can see also the precipitation. For instance, in this case, number of events with rainfall exceeding 90 percentile, 90% number of events exceeding 90 percentile. This is the index that we use. So if you look at this index for El Nino and La Nina in the middle, and then the difference on your right side of the screen, the panel, where the arrow is showing, again, the response is different. You see, blue is negative. That means La Nina is greater than El Nino. The number of events with rainfall exceeding 90 percentile heavy rainfall for this part of SADC region is more than during El Nino period, which is as expected, actually, but here the red ones are the opposite. A dry condition is prevailing here. So in short, what you can say is climate change is affecting rainfall. Yeah, it's true. But this signal, this change that we have noticed, which we attribute to be climate change, can also be partly explained by processes that is more of a natural, because ENSO is interannual natural variation. You cannot stop. It's not coming from climate change. It is there every time. Just we understood about ENSO maybe in recent times. We are aware of it, but it's a process that is there in the past, not because of climate change. The only thing that you could consider is we have to look also because ENSO itself is part of the climate system, so it's not isolated from climate change. So the impact of climate change will also affect the strengths of warm and cold phases of ENSO. In that way, it may contribute to the change we have seen in these three parameters. Otherwise, ENSO on its own is a kind of normal variation. We call it interannual variation because it comes every 2 to 7 years. It's not regular. It's a quasi-periodic event, but it's a part of natural processes. But this natural process is also affected by climate change because this is a sea surface temperature change in the Pacific region, and this sea surface temperature is also very much affected by climate change. So we can argue from that point of view there is some climate-related signal in INSO, but much of it is the natural part. So the change we see in some of these index could also be explained by the natural process, and that's why it's a bit complex to understand climate change. You know, for those skeptics of climate change, they also use this kind of argument. You know, it's not only the side that the geological history of climate change, but they also cite some of these complex processes because you cannot disentangle, you cannot uniquely isolate processes from each other because the atmosphere or the climate system is an open system. An open system, you cannot do a controlled experiment. You can only apply a very systematic approach to really make conclusion. That's why there is some room for skeptics of climate change to argue in the opposite sense. So this is again the INSO influence on temperature. Basically, the INSO influence on temperature. Earlier, we have seen the INSO influence on parameter or indexes that describe precipitation, dry day persistence, continuous wet days, and percentage of events with rainfall greater than 90 percentile of rainfall. These are precipitation event, but here on this slide we see again the temperature events. We have seen these heat waves, mean temperature, interannual temperature range, and how do they behave during El Nino and La Nina. Yeah. So the first column in this slide is the El Nino composite, and the middle one is the La Nina composite, and then the right on your screen is the difference between the two. First column minus second column gives you the third column. Clearly, if heat waves responds in the same manner during those INSO phases, warm and cold phases, you should see the same color. If it is red, it should be red everywhere. But here we see two polar colors, dipolar colors, yeah, red extreme and blue extreme. Red extreme is plus, blue is negative. That means wherever you see blue and you see red, the two regions are responding to INSO differently. So blue means now the La Nina heat waves duration in La Nina is more than El Nino time. Usually we know that La Nina is a cold phase because the temperature is low during La Nina. El Nino is a warm phase, temperature is supposed to be warmer. So the chance to get extreme heat waves is more normally during El Nino. But what you see here is not true, not 100%. It's true everywhere where you see the red, but it's exactly the opposite where you see blue color under panel C. So obviously this is a very complex, process. And for the mean temperature, again, the El Nino composites D, E is the La Nina composite of mean temperature, and on the panel, they look more or less similar, but you can see actually there is some difference when it takes the difference, because the difference is small, of course, but you can see clearly there is a difference. There is a difference. So temperature, mean temperature is actually warmer during La Nina over this part, and also over the eastern coast of the SADC region here, Mozambique, South Africa, on this side of the ocean, yeah? And areas in Botswana, Namibia, parts of Zimbabwe and Zambia, and parts of Angola, much of South Africa, you see red color. That means El Nino during those periods, years where there is El Nino, the temperature, the average temperature is warmer than years when there is La Nina. That's exactly what it shows. And we can continue looking at also the interannual temperature range. The funny thing is, again, if you look at the two composite, the El Nino composite G, the La Nina composite H, in terms of color, they're more or less similar. But when you take the difference, again, you see some differences. And annual temperature range is blue. Blue means La Nina temperature range is increasing during La Nina as compared to El Nino years. Red means temperature difference between maximum and minimum is increasing during El Nino. That's what it means. This is basically a kind of trying to make some conclusion to see what is the response. Because in climate science, the basic laws plays a great part, but the interaction is so complex. Data science, information that you get from the data should help you make the conclusion. Of course, it shouldn't be contrary to the science itself. You should consolidate what you see from the data with what you make out of scientific theories. Yeah, scientific theories. So this work is already presented in a conference in June. I gave a talk there just recently, and yeah, it's not yet published. We are going to publish it in the future. So all in all, what I would like to say is that yeah, climate change is causing changes in different ways, and sometimes it's not as you expect them, because there are other factors that come into play, and as a result of the fact that the atmosphere is not a closed system, it's an open system. Atmosphere interacts with land surface, with water body, and even with the space, yeah, with the sun. So it's an open system where you cannot control. A unique conclusion can be made only in a physics laboratory and in a biology or a chemistry lab where you control your sample, yeah? You put them there and you change certain things and you see the behavior, the changes, because you know what you put in and you can see what comes out of it. But in this case, you don't even know, all in all, what is playing into the system to provide you this kind of output, okay? So I'll quickly move to the water quality, and then I'll take your question. The rest, I think it's about hydrology in the SADC region. That will be covered also by Marila tomorrow. So I'll leave for it. I thought that I can give you some overview, but looks like I'm not going to make it to that point. So before I take your question, let me cover the impact of climate change, climate extremes, or hydrological extremes on water quality. Yeah. Here, well, as you know, I'm making the same general statement: climate change is affecting the global hydrological cycle in its totality, yeah. And increasing temperature can have impact on the water quality. What this degradation could include, well, the water quality could be affected by flood, could be affected by droughts, could be affected by different cases. For instance, industrial accident could also cause water quality degradation, but this is basically because of human activity. So we have also agriculture. Nowadays, we use fertilizer. Our soils are not anymore generous enough. So we have to provide them with something, which is phosphorus, nitrate fertilizers. And usually these are basically, once they enter water, they are pollutant. They are pollutant. They are affecting the water quality. So there is the impact of climate change is also affecting water quality, and it's a very serious problem. This is one example where you can monitor water quality. I'm presenting this. This is actually in Eastern Africa, in Ethiopia. We look at lake water quality. The bottom image is a satellite image of a lake. You can see it's a RGB color, a false color image, but this image can be used to infer water quality. Basically, water color index. So the color of the water tells you about the qualitative quality of the water. It's not going to be quantitative. We are going to use index. Yeah, we are going to use index to measure phosphorus and other things exactly. You have to have a sampler. Yeah, you have to take water sample, do the analysis in the laboratory. But from remote sensing, we can at least give a qualitative information about the water quality. So here, this is the place, as you can see on the top left corner. You see the lake area and the topography, and then the next panel is the whole African country, and you see where this lake is located. Down at the bottom in the first panel is Ethiopia. So we looked at the satellite image from there, and we tried to really estimate what's known as FUI index. It's called water clarity index from MODIS satellite. It's a MODIS satellite. We use this. We have to combine the different bands, the visible band. MODIS has a different band. It's called B1, B2, B3, B4, B5, B7, and so on. And all of those bands have different sensitivity. Some are in the visible. The RGB bands are visible bands, red, green, and blue. But the other bands are in the infrared and in the short infrared. If you combine them, you can define what's known as FUI index. FUI index is a water clarity index. You can go and read them. You can have this information from this paper. You click them. You can really download them. It's free. It's an open journal paper by my student. What you see here on the right side of your corner, you have 5 panels with blue and red color. It represents FUI index, and for 5 cases, we look at extreme precipitation, above normal precipitation, and we looked at the index when there is normal precipitation, below normal precipitation, and extremely low precipitation. So you can see clearly that red means the water clarity is poor. It's the water, that means the water quality is bad. blue means the water quality is improving. So as you go from extremely low precipitation to extremely high precipitation, you see that the transition from dark blue, good water quality, to red, deep red, to bad water quality from the satellite. Yeah. We also looked at how that surface runoff affects water quality. The bottom 5 panels shows extreme heavy runoff, above normal runoff, surface runoff, and normal runoff, and then below normal runoff, and then extremely low runoff, surface runoff. So again, you see the quality. This is a very qualitative index. It only tells you whether the water is clear or highly polluted. The clarity is very low. So when the index number is increasing, clarity is getting poor. It's a very turbid water. And when the number here on the color bar is low, then the quality improves. Water is more clear, yeah, more clear. You can see about the theory of water clarity or water color from this paper. There's a lot of detail that you can even use if you want. And of course, I also provided a link to more general lectures on remote sensing, use of remote sensing for water quality, even for agriculture. I don't think you are interested in that area, but for hydrology, if you just click on the link below here, this is a training from NASA, which tells you how to use the data, how to process some of the water quality parameters. It also tells you about chlorophyll A, turbidity parameter. There are many parameters that describe the water quality. So you can go there and explore further. So basically, we see extreme precipitation is affecting water quality, which is related, of course, with runoff. The more extreme precipitation is, the more surface runoff. So it's not surprising to see that the extreme precipitation and extreme runoff, surface runoff, have the same impact on the water clarity from this region. Of course, water quality parameters are not only clarity. There are other physical parameters. For instance, on this panel, on the left side of your screen, you see water quality, physiochemical parameters, and then biological parameters. And the physical parameters are such as pH and dissolved oxygen and temperature, dissolved organic carbon, nutrients. These are under physiochemical parameters. Macro pollutants, these are inorganic parameters such as metals, pesticide, organic parameters. Pharmaceuticals, they fall under the physiochemical, of course. These are the parameters. You can measure them actually. You can go, if you have a sampler, you can sample them and you can test for presence and or even quantify the amount of this water pollutant in water in a river or in a lake. Biological water parameter indicators are cyanobacteria. These are pathogens actually. Cyanotoxins are green algae, diatoms, fish, and other things. These are part of the biological parameters that one can really derive. But what we are trying to show is, in the previous slide is, in fact, some of this can be derived from satellite on a larger scale, because you don't have to go to the field, you don't have to collect so many samples and analyze, because you need chemicals, you need facilities. That is more costly than using satellites, and at the end you get the same result. At least you know what is the water quality, at least the range of the water quality. The parameters that affect this parameter, like the pH of the water, dissolved oxygen, temperature, are many. Climate factors, drought, temperature, increase, and rainfall, as we have seen already. Drought and temperature increase. For temperature again here, In the river, in the lakes, you can do this kind of analysis. Dissolved organic carbon, temperature and rainfall, streams, and in the lakes, you can do all of this analysis, yeah, all this analysis. So we only looked at water clarity index, but one can go beyond those things and try to understand water quality from satellite image, because satellites are everywhere. I've shown you this morning. These are a lot of resource. That's why nowadays people talk about big data. Where the big data is coming? It's coming from mostly from satellite measurements. They are very huge, actually, very huge. When you do the exercise I gave you, you realize that the data is too much, and in some cases, if you are not careful, difficult even to make any conclusion, because you have so many data that shows you somehow in a way it looks contradictory, because of course they are not contradictory, but because of your knowledge and understanding, they may appear contradictory. So it's good always to work with a small data, try to understand, have the science, and then move forward. This is another study done in terms of, for instance, oxygen, dissolved oxygen, and pH. It is in the Meuse River. It's in the Netherlands. This shows how heat wave of July 2006. This is a single event. The heat wave of July 2006 is a famous heat wave. I don't know. Most of you are young. Maybe you don't even remember what happened. It is a big news. A lot of old people died in Europe, particularly in France. You know, the life expectancy in Europe is very high. You'll find a lot of people above 80, 85 years old. Yeah. The pyramid, the population pyramid, is reversed in the other region. So, but this heat wave have affected a lot during that period, and not only killed people, but it also affects the water quality in the region. And here is another example where some of the elements like ammonia, fluoride is affected because of a river discharge. When you have a low flow, the blue shows the flow rate. The flow rate, if you have this high flow rate, you can see by sharp peaks here of the curves on the right side of your screen, and minimum flow is where you see flat close to the zero line, yeah, from January 02 up to January 05. Okay, and you can see the amount of ammonia and chloride measurement given in microgram per liter. This is actually not from satellite. They went directly to the river, picked the sample during this period. Wherever you see high flow, the amount of ammonia and fluoride in the water sample has gone down, because they don't stay there. Water is not stagnant. So the pollutant is easily distributed and diluted. Whereas during low flow, you see the peak in fluoride, which is orange points, orange scatter point, and ammonia is blue. You see minimum flow, maximum heavy metals here. And so you can do this, and of course there is a way to use satellite to understand the water quality. This is just another supporting evidence from our study that shows droughts can affect the water quality. As I said, red means bad water quality, or the clarity of the water is very low, is highly turbid. And when it goes to blue, the clarity is improved. So you can see normal drought years, moderate drought years, severe drought years, extreme drought years, they have different impact. Even within drought years, the normal drought years still are able to have a relatively cleaner water quality in the lake. But if you move to moderate, again, more or less the same, except some areas. But if you go to severe drought cases, you start seeing a lot of deterioration in the water quality and so on. And wind speed is another parameter that affects the water quality. High wind speed means a lot of sediments from neighboring areas will be transported to the lake, and the clarity water will deteriorate. That's exactly what you see. And it's amazing that you can see this from satellite. Naturally, we know from your experience, if there is a lot of wind, it will carry a lot of dust. And you may think it doesn't make an effect on the lake water, because this is the lake, big lake, and nobody expects that it's going to change the water clarity of the lake, but it does. As you can see, wind speed can make a change in the water clarity, on the water purity, even if the lake is big enough. Groundwater somehow can also be affected. It's not like the surface water by some of these pollutants, but there is to some extent this is also affected by some of the pollutants such as nitrogen, phosphorus, because it can easily intrude into the groundwater. They don't remain on the surface. So you can have nitrogen and phosphorus contamination into your groundwater. And along coastal areas, during drought year, for instance, there is a possibility that water can intrude from the sea into your aquifer, because of the water table, and you can have very saline water inland. So groundwater is not immune to changes, even though to the extent to which it is impacted by climate change is not the same as surface water. So I think at this point I will stop, because Marilla will continue for the SADC, and it's important to engage you on discussing what you did understand, or what you want to get, what you want to have more explanation on. So, coordinator, you may open the floor for discussion. Thank you.
Thank you, Prof, for your presentation. The floor is open for questions. Yeah. Good morning, Prof, once again.
Good morning.
Thanks for that lovely presentation. I want to find out something, Prof. I've developed an interest in the connection of ENSO to precipitation and temperature. I want to push it to a local level. But I like some basics about ENSO, so I wanted to find out if there's any literature or resources you'd advise I try to go through just to build my foundations.
Can you repeat? I missed the first part. You are interested in which part?
In the connections between ENSO and precipitation and temperature. But I lack some basics. I've just developed this interest. So I wanted to find out if there's literature, very good literature that you can recommend. I can go through my foundation.
Yeah, actually, I have already shown the link, but I'm going to send you today through Ronil about 5 or 6 references that I listed. I went to donate. I don't own them, but I'm doing something illegal. But here in Africa, we cannot survive without doing that. So I'm going to share, I don't know the policy of NUST here in BUST at my university. Formally, officially is illegal to get a document without permission. But if it is, since you are going to use for your own personal things, I'm going to share some of the materials, and you can go through them. Some are very basic, and yeah, that's what I can say.
Thanks a lot.
Okay, any contributions, comments, questions, colleagues online?
I don't see any comments from the online chat unless there's something that is, yeah, it doesn't look like there are any inputs, but just to appreciate the knowledge that has been imparted to us today. Thank you, Mr. Coordinator, back to you.
All right, thank you. I think in the absence of any questions or comments, we can call it a day of this session. Thank you.
Yeah, thank you. I think I just want to tell you that you have more lectures coming up tomorrow. Marilla is going to talk about vulnerability, and I think she's going to talk very important things on her side, particularly in the social component. From what I see, the audience is very diverse, and don't please attending those ones. And also, Dr. Luna will also give a lecture on Friday, and I think that will conclude our discussion. And if you have any follow-up questions, help in this regard, all of us are ready to help you. I mean, even you can contact us for further material, apart from what I'm going to send you jointly as a group, so that I can answer case by cases. Thank you so much for your attention, and that is it from my side. Thank you. You are muted, Rainy.
No, I just want to say thank you so much, Professor Tidu, for really committing 2 days to engage with our students. We quite appreciate this platform, and we welcome the invitation to continue with the conversation and engagement with you, even after the seminar has been concluded this week. Thank you so much for your efforts, and we appreciate your time and knowledge.
Yeah, thank you. Yeah, I think initially I was not optimistic, but it appears that everything went very well. I hope we keep engaging online, by email, whatever. Thank you.
Thank you. Goodbye.
Yeah.
Thank you, colleagues.
Yeah.